In accordance with the customs of this university, I open the ceremony with a prayer. Spiritus Sancti Gratia illuminet sensus et corda nostra. Please be seated. So before opening the session, I should like to thank the professors and others that are going to participate and come from other universities. Let me start from Professor Ekkes Brück from Delft, Professor Palstra from Groningen, Dr. Caron from the MPG Dresden in Germany, Professor Coehoorn from the TU Eindhoven, and Professor Havenith from Groningen. So, I now give the floor to the candidate for the degree of doctor.
So with the permission of the Council of Deans, and in order to obtain the degree of doctor from Radboud University Nijmegen, I like to defend in public my doctoral thesis entitled Treatise on Magnetocaloric MnFeSiP compounds, a first principle study. So to begin with, so if you look around the conventional refrigerators around us in domestic applications or in industrial environment, there are certain problems with these refrigerators or fridge that I've listed here. For example, the efficiency are quite low for these devices, so it consumes a lot of power. Also, these devices contain environmentally pollutant gases, and when we dispose them, they are emitted in the environment and pollute them. And they are noisy, we all know, and it's difficult to scale these devices, so we cannot make it infinitely smaller without compromising the efficiency. So, as a result, this is not a favorable choice of refrigerations. So, to solve this problem or issue, scientists did a lot of research, and in 1997 came the breakthrough when Pekarsky and Snyder they discovered giant magnetocaloric effect. So, using this effect, they are able to cool the refrigerators in the room temperature, and I have shown a small diagram how this thing operates. So when the material in the left here, a magnetic material, is put inside a magnetic field, the spins aligns along the magnetic field. And since this process is done adiabatically, it heats up, and after releasing the heat slowly, when the material comes again in the room temperature, and then the magnetic field is removed from it, and because of the reverse process, it cools down. And at that moment, it absorbs heat from the refrigerators, and it cools down the device, the refrigerator, or air conditioning system, anything. So if we do this process repeatedly in a circular operation, then it can be used effectively as a replacement of the conventional refrigerators. So there are certain advantages of this process compared to the conventional one. For example, the efficiency is of course higher, and since it's solid-state cooling device, there is no gas involved, so it's not able to pollute the environment. They are silent in operation, and it can be easily scaled. So it seems it's a better choice compared to the one we are using right now. So after the discovery in 1997, there is a lot of research focused on this field, and here is the landscape of all the materials in 2012 that have been shown in this graph. So on the x-axis, we can see the temperature of operation, and with the y-axis, we see the effectiveness. So the mostly high efficient devices or materials, it's contain a rare earth element, and to replace that, or to solve this issue, this material was actually primarily focused, which contained mostly abundant materials that can be found in nature. So this is a better choice, and my whole research is also based on this material. So in this series, this phosphorus germanium, it can be replaced with other non-metallic elements. And this is one example where one of this material is going through a magnetic transition at the Curie temperature. So from low temperature to high, the material goes from a higher magnetic moment to a lower magnetic moment. And so it goes from a ferromagnetic phase to a paramagnetic phase. And to model this kind of behavior, we need to model the ferromagnetic phase and paramagnetic phase separately. That's, and now I'm going to show how do we do that. So to model this ferromagnetic phase, or FM, it's very easy. So we take the unit cell of this material. Here, these are the atoms, the circles, and we put the magnetic moment along one certain direction. So this is ferromagnet. However, the paramagnetic moment is very difficult, paramagnetic phase difficult to model, and there are various theory, various ways to do that. However, we only consider the simplest one, where we take two unit cells on top of each other with the opposite magnetic moment. So the total moment is 0. So this is the simplest one. However, for different situations, we use more different kind of alignment like this or even this. So this is the way that we model the ferromagnetic phase or the paramagnetic phase. So using this kind of modeling methods, in 2011, Professor Robert Groot and the team, they first came with the theory of mixed magnetism. So as the outcome of this theory, they predicted there is a change in electronic distribution around this iron atom, which is responsible for the high efficiency of this material. And at this point, I started my PhD, and for 4 years of research, it resulted into 5 chapters in my thesis. So starting from chapter 2, if I just briefly describe what is in there. So in chapter 2, we have shown that in this charge density graph that I have shown before, there are introduced some foreign elements like some other transition metal elements. We put it in there, replacing the element which was already present there, like chromium, manganese, cobalt, etc. And we've shown that the charge density looks way different than each other, although they have very similar electronic structure. So these are used to optimize the material properties for their magnetocaloric applications. Also in the same chapter, we also discussed the mechanical strength of these materials. Since the material go through from one phase to another, it needs to be strong enough so that it doesn't break down. So it's very important that we calculate the mechanical stability or the strength of this material. And the simple way to do that is to find out the elastic modulus of this material. So elastic modulus can be bulk modulus, shear modulus, Young's modulus. We calculated all, and we described and predicted their strength. In the next chapter, chapter 3, we describe the thermal properties of this material by means of phonon calculations. So here is one of the results, and from this picture we have shown that there is a Curie temperature around 410 Kelvin of this material, and also it exhibits a latent heat of 20 kilojoule per kilogram, which is also very close to the experiment. And also we have definitely proved that it goes through a first order transition. In the next chapter is a collection of 3 different studies where we compared directly with the experiments. So starting with the first, we described that we have shown this picture before. So this is the unit cell of the material and all the atoms sitting here. So we have proved here that the silicon atoms over here, it occupies the particular site, which is the 2C site. So from this picture. In the next part, we describe the similarity between the experiment and the theory charge density, theoretical charge density, and show a remarkable similarity between these two. And in the third chapter, we have shown the similarity between the XMCD spectra from calculation, the green dots, the experiment, the black line, and the multiplet calculation. In fifth chapter, we try to predict the phase transition between hexagonal phase to orthorhombic phase by means of pressure. So the results are shown here that it goes from a magnetic transition at a certain pressure, and at the same pressure it goes through an elastic transition. That's why it's called a magnetoelastic transition. And in the final chapter is also a collection of various studies. Here I have just shown one for example. We use a spin orbit coupling calculation, and we find the anisotropy constants. So we have shown basically by the change of x, the concentration of iron here, how the magnetic moments goes from the parallel to the perpendicular direction of c-axis. So there comes to the conclusion of this small talk. So basically I've discussed the conclusion after every chapter, so I just picked up the most favorite one of mine. So this is the similarity between the experiment and the theoretical charge density calculation. So here we definitely proved
Could you speed up a bit?
Yeah, that there is a similarity between the charge density and this is also a manifestation of the mixed magnetism. So I'd like to finish my talk here, and thank you very much. Okay, so having presented the summary of my doctoral thesis, I return the floor to the rector.
Thank you. I now give the floor to Professor Groenenboom, who will start the opposition.
Thank you. Dear candidate, I'd like to start by congratulating you on a very nice thesis. As you know, I'm a theorist myself, but working on molecules rather than materials. And I'm very much impressed by the complexity of the problems that you work on. I'd like to start the discussion with chapter 2, where you study the effects of dopants. And on page 15, you claim what seems to be an important result of this work, that I'll read from your thesis. Our study establishes the fact that doping with boron significantly increases the elastic constant as well as the mechanical stability of the material. And that may be a very important result also for practical applications. But then I read on page 25 that there was in fact also an experiment by Gilles. And so my first question is, what came first, the theoretical prediction or the experimental result of the effect of boron?
Okay. Honored sir, to answer your question, I think the experiment came first. So there was a certain trend from the experiment which shown that the small amount of doping like boron or sometimes carbon also enhances the mechanical stability of these materials. So after that I was inspired and from Professor Brück, and he suggested me to actually work on this and to find out the reason.
So maybe then I can ask, because as a theorist, of course, the first thing you want to do is see if your theory matches an experiment, and if it does, you're always very happy. But then the obvious next question is, presumably by doing the theory, you'll learn something, some rules that you can then actually use to suggest new experiments or new materials. And maybe that part you can explain to me a little bit. Now you reproduce this effect of the boron. What kind of general insight does that give you to actually further the goal of enhancing the magnetocaloric effect?
Yeah. So we replace boron at this non-magnetic site. So definitely this is a best choice to choose some non-magnetic materials instead of magnetic materials, as of course that was also the inspiration of the experiment. And the size of these atoms really it matters in case of doping. And since so to be truthful, I should have compared it with other materials, also doping with there, and see the effect. So in this particular study, I did not compare it with various different dopants there. So for this particular aim of this work was to actually produce, not to further,
Maybe I can ask a little further question on this, because now, of course, these calculations take time, so you start with one material, obviously, and but now if you would actually do a lot of calculations and then find that specific sites or specific atoms have the desired effect, would that really work? Because then I wonder, can experimentalists actually make the material, or can they just put an atom on a specific site, or do you also need to help with that? What is possible in the synthesis?
So for this particular series of material, it's very versatile, and it's also very nice and very flexible to dope with any kind of materials within the structure. So basically this is a nice start for the experimentalists also. They can start with various composition at the beginning. And well, for the experiment, from the theoretical point of view, it seems it's a bit more difficult than the experiment, because if we actually try to dope it with any single atom there, you need to consider at least 8 times bigger unit cell. So for a more complex composition that also been done in experiment, it's actually not possible in theory. So in theory, in turns, it's more difficult than experiment in this case.
Okay, so it's not like you're going to give them a list of what to try, basically.
Indeed, yes.
All right, okay, thank you very much for these.
Thank you very much. So we proceed with Professor Brück.
Hartelijk dank, mevrouw de rector. Dear candidate, I will continue with chapter 3, and I was really amazed how accurate you could calculate the lattice parameters of the system, and actually also you got very interesting result, or very close result to the experimental findings of your critical temperature. And also the latent heat was almost to the spot, and if you would consider that you get even closer with your TC to the reality, that latent heat would even be better. So everything goes the right direction. On the other hand, when we change a little bit the composition of our system, it will go to a second order phase transition. Would you dare to say you can as well calculate in this system very nicely the TC, or is there some more difficulty? Or so I would like to discuss with you about that.
Yeah, honored sir. So I also thought about this before, about how to predict from a first order to second order transition. And well, from picture 3.6 in the thesis, we see for the first order transition, there is a sharp peak in the specific heat. And according to our calculation, if it's second order, then we don't see this sharp peak in there. And if you go to picture 3.5, the first part of the picture 3.5, the slope of free energy should be same at near the Curie temperature. So essentially, it should be like that if it's a second order transition, if I work with some second order material. However, I personally did not do this calculation, and I'm not 100% sure that it can come in this way. So it's definitely trial and error method. I can try it and see if it is coming there. But I'm not 100% sure that it will B definitely prove a second order transition in this case.
Okay, but if you would just think about putting a composition into your computer where you have experimentally we would find a second order phase transition. So, for example, put in a lot more manganese into the system would give us the second order phase transition with the same silicon phosphorus ratio.
Yeah.
What would you expect to see in your ferromagnetic state and in your paramagnetic state?
Yeah. So in that case, I would expect that that the phonon spectra would look much different than it is right now. So there would be a less change in the phonon frequency and the phonon spectrum in general, and so that these both graphs, both free energy slope will remain constant, fairly constant near the transition, so that we get not a sharp but a broader peak there.
Okay, but more particular to the ferromagnetic state and the paramagnetic state, so what is there the difference?
Okay. Well, so also the structure that we only consider here the lattice parameters, which is only two sets here. So there we probably need to take more sets in this case, because it's not a sudden change. So here we consider one is below the transition, one is above the transition, but there in this case we need to take a bit more continuous. So we also need to have some experimental input in this case, how the transition occurs, and we probably need to do more calculations.
Okay, maybe when you look at your lattice parameters,
Yes.
you see that the ferromagnetic phase has a larger volume than the paramagnetic phase,
Yes.
which is contradicting, in principle, the thermal expansion statement, because normally a material always has small volume at low temperatures and high volume at high temperatures. And in your calculations, you show, no, the low temperature phase has a higher volume than the high temperature phase. Will that maybe alter when you have the other compositions?
Well, to the first part, I guess if we look at figure 3.4, we calculated the volume expansion there. The second part of figure 3.4, we see that the volume is basically increasing when we consider the quasi-harmonic approximation for this material. And for one each phase, but since it goes from a transition, there is basically a jump there. So the red line is the ferromagnetic one, and the blue line is the model paramagnets. And yeah, if we consider only one particular phase, it's basically the volume is going up, so there is a volume expansion. However, because of the first order transition, there is a jump from a higher volume to a lower volume. So yeah, this crossing might be at lower temperature if it were a bit more accurate calculation. So that can solve this issue with the contradicting with the experiment. But to answer the second part of your question, I think yes, since as I was trying to explain that instead of taking only two sets of volume, or two sets, one ferromagnet, one paramagnet, we probably need to consider more sets in between. because the transition is broader also. It's not at a certain temperature or a certain magnetic moment, magnetic field. So since the magnetic transition is broader, we probably need to take more than one phase, more than one arrangement of magnetic moments.
Do we still have time?
Couple of minutes.
Okay. Now, so what I'm in principle aiming at is when you have here your two, let's say, structures. They are the same structure, but still you have the high temperature structure and the low temperature structure,
yes.
You could say, because you have different COA ratios and so on. And in principle, the first order phase transition is due to the fact that the TC of your low temperature structure is higher than your phase transition occurs.
Okay.
So then you jump from your high temperature structure into the low temperature structure below TC, and therefore you get a sudden increase in magnetic moment, and you have much more magnetization than you would expect in a slow or gradual second order phase transition where you go from at the normal TC into your system.
Yes.
So what would characterize then the second order phase transition material? So to avoid the jump, what would be the necessity to create?
Yes. First of all, there shouldn't be any latency involved there. So the latency found there, it should be 0, experimentally at least. And in principle, from the structural point of view, so from the calculational perspective, I think there should not be any crossing in the free energy, and it should be more or less the slope should be more or less continuous near the transition, and but what the precondition for that? Yeah, that one is the main question, I know, but I don't have a definitive answer with me right now for that, the precondition for the second
Okay,
order.
so you should do some more calculations on aspects. Okay.
You're satisfied with that, okay. We proceed with Dr. Caron.
Thank you. Dear candidate, first of all, I would like to congratulate you for your work in helping us understand what we see experimentally. And to begin my discussion, I take cue more or less of the end of section 4.2 in page 48, where you talk about the D bands of the metals and the P bands of the non-metals in iron to phosphorus-based compounds, and how in the exchange of electrons between these two affects the phase transition and the properties. So from the point of view of the silicon and germanium materials, it makes us understand quite well that you're changing the number of valence electrons, and that changes your properties. However, when you look at arsenic, arsenic has the same number of valence electrons as phosphorus. So changing your phosphorus, arsenic, silicon, arsenic the ratio doesn't change your number of electrons in this interaction. So one would be led to believe that in the case of arsenic, it's more of a structural effect, while in the case of silicon and germanium, it's quite clear it's not. So how do your calculations conciliate these two things? Because it has to be a mixed effect in both cases. So That's my question.
Yeah, according to my experience here in this case, it's always the site and the material, the elemental. Sorry, honored madam. This is the first thing that we need to always understand when we look into these material properties. First, the property of the site, and secondly, the elemental property of these materials. So, in this particular case, the 2C site and the 1B site, they definitely have a different property because of the location within the structure. However, the arsenic, they have a similar electronic structure, the outer shell. However, they have a different radius. So that also matters in this case. And yeah, so instead of silicon, when we look at arsenic, I think according to me, this the radius of these atoms, it has effect to have this different. Yes.
Okay, so the thing is with arsenic materials, especially when you put physical pressure in, it doesn't mimic the effect of adding arsenic or removing arsenic.
Mm-hmm.
So one could say, okay, it's not a volume effect, but I guess you have to tweak the, let's say, the interatomic distances to increase hybridization between these orbitals and...
Yeah. Yeah, since the lattice parameter itself also has an effect in there.
Yes.
So, definitely, it's the suggestion is correct. I think the hybridization, it changes instead of having the similar electronic structure because of the distance. We can actually see this in a different scale when we look at the crystal field splitting in the same thesis at the last chapter.
Mm-hmm.
So everything has a certain effect there. So the elements there, the bonding elements, the distance itself, and also the angle between the atoms. I actually did not do the calculation with arsenic. However, I think this is one of the effects that is responsible for this pressure effect. I mean, you do not see the difference.
Okay, nice. I still have some time?
Quick one, very quick.
So I go straight to chapter 5 to talk about pressure.
Sure.
So if you want, it's page 74 and 75, where you show that at 20 GPa, the structure likes to jump to this orthorhombic phase, it seems to me not to lose the magnetic moment. Did you look into the magnetic ordering in the orthorhombic phase?
Not really. We always took the ferromagnetic structure in this whole calculation.
Because iron 2 phosphorus pure is known to go into an antiferromagnetic phase at 1 GPa.
1 GPa, okay.
Yes. So I was a little bit surprised not to see that here, and also that's why I wanted to know and that transition is actually isostructural, so it remains hexagonal, but it goes antiferromagnetic.
Okay.
Before it goes again ferromagnetic, and this obviously moves down.
Uh-huh. So yeah, definitely. So first of all, I did not look into that extra phase there. And as you say, there's much more phases. So instead of having only 2 curves, there are probably a mixture of various different curves. And we finally, to have a complete study, we need to actually, or to reproduce the experiment, we need to have all these phases that we see during this pressure, applied pressure. So this particular work is only focused on only these 2 structures, the hexagonal and the orthorhombic, and also in some sense the change in the hexagonal structure at a higher pressure. But of course, if we add an extra phase there, we can see extra transition.
Okay.
Yeah.
Okay. Thank you.
You are satisfied. Okay, thank you. We proceed with Professor Palstra.
Thank you, mevrouw de rector. Dear candidate, I also read your thesis with much interest. You've done very accurate calculations, and you've gone to get extraordinarily accurate results on some of your calculations. I would like to go with you. I'm a simple experimentalist, so I would like to go with you to some of the assumptions that you made for the interpretation of the results. So first, you state that you have used very accurate X-ray diffraction analysis to analyze the position of your atoms. Now, you did not specify what kind of X-ray, but I assume that it's single crystal X-ray diffraction. But assuming that this is what it is, my real question is, you show that your charge distribution is non-centrosymmetric. And one of the things in X-ray diffraction is that almost everyone, 99.9% of all experimentalists, we use form factors which have a centrosymmetric charge distribution of the atoms. So how accurate is your structure determination really now you have an acentric charge distribution?
Honored sir, all the experimental results that I've used here are, I have taken as an input for my calculation the structures. So in particular that you mentioned the electron density picture in this case. So here we see this the non-symmetric charge distribution around the iron atoms. And this is actually the difference in the two different magnetic structure, let's say the ferromagnetic and the paramagnet. And there's also a dependency of the shift of the atoms. So it's not only the difference on the electron density, but also the shifting of the atoms. So so it is much less pronounced in reality that it's visible here. This is the first thing, and the secondly, it's not a single crystal X-ray diffraction as far as I know. It's from a powder X-ray powder sample. So this so maybe you. Can you please comment on
well,
it? Yeah.
The question really is, since it does not really matter what kind of X-ray diffraction you use, you always use atomic form factors.
Okay.
The atomic form factors always assume a centrosymmetric charge distribution.
Okay.
So your X-ray patterns should be looked at with a grain of salt. I mean, people claim a higher accuracy than they actually can produce.
So, if I understand that, so you mean the charge density around the atom should be the symmetric around the atoms all the time.
It is, by definition, if you use an X-ray diffraction analysis in powder X-ray or single crystal X-ray diffraction. So if you have a non-centrosymmetric charge distribution, then if you would like to take this into account, you have to use different analysis. This is non-trivial. It's also typically a very small effect because you're dealing with valence electrons.
Uh-huh.
This just as a precaution, then maybe. Don't believe us crystallographers too much. But the more serious part is on XMCD, because in XMCD, this is an experimental technique that is highly accurate, and you show that the results are different from neutron diffraction. And that is what you show on page 66. That you have a different atomic moments for your neutron diffraction than for the XMCD measurements. And you blame this to the surface sensitivity of XMCD. But XMCD is an absorption experiment. And an absorption experiment is highly reliable. It's typically done also in transmission. So its absolute values are highly reliable. And basically there, the theory is based on some rules. And these cannot be violated. So I do not believe your statement that this is based on a surface effect.
Yeah, actually, this is the same idea about from my side as well. So according to me, it's also not a surface effect. So it's some other researchers, they claimed it to be a surface effect. although there is that that thing that I observed, that if we just sum over the local moments of the iron and the manganese itself, it does not add up to the total moment of the material of the unit cell itself. So that is my observation, and so I did not personally made any explanation there. What is the reason behind that? So this is just observation, and I mentioned that other researchers they claimed it to be a surface effect. Although according to me, yeah, it's probably not the surface effect. It should be something else in there.
Okay, you
Yeah.
agree with me that?
Yes.
Okay,
Yeah.
very
Yeah.
good.
Satisfied with the answer?
I'm very satisfied. Thank you.
Okay, we proceed with Professor Coehoorn, please.
Thank you very much. Thank you very much, Mrs. Chairman. Dear candidate, I would like to discuss with you, firstly, some results of you in Chapter 3, where you, I think, did very interesting calculations of the ordering temperature, or actually the phase transition temperature of your system. What you did is that you included phonon effects, and you included the results of magnetic calculations for two magnetic states, one ferromagnetic ordered state and one antiferromagnetically ordered state. And I was wondering concerning that last point, whether you included enough effects. In the first place, if you consider magnetic excitations, not only transverse excitations, so rotations of magnetization, magnetic moments, but also longitudinal effects. So changes of the size of the moment without a rotation can be important, and this is well known already for a long time. It results in the so-called stoner theory for the Curie temperature. So I was wondering, did you consider that effect as well?
Honored sir, in short, I did not include that, but to explain why, because to start with, because the whole chapter is written as a step-by-step way. So first, I included the phonon calculation, simple phonon calculation, doing for both phases, the ferromagnetic and the model paramagnetic phase. Secondly, to include the complexity, increase the complexity of this calculation, we added this quasi-harmonic approximation to find the volume-dependent effect. And in the third approximation, we added the different magnetic ordering. Let's say within the paramagnetic state, there can be configuration entropy that's we included. So as a third approximation. So that one is suggesting is probably can be used as a fourth approximation, which can further modify the Curie temperature from 410 Kelvin close to the more experimental value like 300 Kelvin. So yeah, it should have been done, but for this particular study, it was not done.
So probably you had a certain motivation why not including this, because potentially, leaving away a certain effect can give rise to a totally different prediction. So what was your motivation not to include this effect?
Well, yes. So first of all, the complexity. So it was already been very complex to add these three effects, and it was the trend was actually very obvious that when we take you are right, it can actually go to a different prediction. It could have been, but after adding all these second and third assumption, it was going more towards experimental observation. So we decided to skip that one for the moment and keep the space open for the next study.
Yeah. That is maybe extremely dangerous to be to let you guide in your decision making by what is already known from experiment, because maybe with a with an incorrect theory, maybe you predict then of course after the experiment has been done something which might not be predictive for another case. So let's then continue on this theme. So you nicely included at least two magnetic configurations, but in earlier work on calculating ordering temperatures, people have considered usually approaches in which many different antiferromagnetic orders have been included in the calculation, so that using a Heisenberg model, Heisenberg interactions between spins in the system, pairwise and maybe also next nearest neighbor interactions have been deduced from the simulations, and then the energy effect of many different configurations of antiparallel systems could be deduced from only a few calculations. But although only a few, more than two. So I was wondering, did you also consider that approach?
Yeah, sorry. That is, of course, a valid approach, and I have seen papers following that particular approach. And but in this study, we use relatively simpler approach considering the complexity of the calculation and the size of the calculation. So we partially solved it by taking this configuration entropy, where for that particular size of the unit cell with 4 unit cells arranged in the xy direction, we took all the possible magnetic configuration for that. Statistically, we included that one using the configuration entropy.
Yeah, I think that's good that you have done that, but there could also be an energy effect on top of the entropy effect, and maybe there are non-trivial energy effects. For example, maybe under some orientation configurations of these spins, even the manganese atoms would get smaller moments, and would be maybe destabilized to a certain extent. So I can imagine that non-trivial effects arise if you consider different configurations of the magnetic state.
So just partially this answer, it can be, so according to my study in a different context here, also included in the thesis, that when we took a different orientation, like including spin-orbit coupling, we see that the orientation of this magnetic moment does not have much effect in the total energy of this material. So, so in this case, if we had considered various different configuration with a different angle between two particular atoms, it will not affect the energy relatively higher in the same scale that we are talking about here. So it can have certain effect, but that's why we neglected this assumption that we did not include it because of the size, considering our experience.
Yeah, so let me see, when you talk about orientation effects, I think what you mean is that you then rotate in a coherent way all the spins in the unit cell all in the same direction, for example, from the C-axis direction, parallel, antiparallel to A in plane direction. Is that what you mean?
Yes.
Okay, so maybe then, because you have raised this point anyhow now, we can go to chapter 6, where you discuss the subject of magnetic anisotropy. And first question that I had there is, how did you actually calculate it? That was not clear from the text. I had the impression that you included the dipole-dipole interaction, so the magnetostatic interaction, but I think in your overview you also mentioned spin orbit, so can you explain better what you did on page, what is it, 83?
Yeah. So in this, chapter 6, page 83, we have calculated this spin orbit calculation for different compositions. So experimentally, there was an observation that the direction of the spin is rotating with the change in the composition of this material, iron concentration. So we try to understand why. So we actually include the spin orbit calculation. We did the spin orbit calculation, and we took here in the figure 6.2 on the x-axis, we have shown that how the direction of the spin is rotated from the c-axis. So all the atoms we rotated simultaneously from the c-axis by that certain angle, like 0 degree, 20, 40, etc. And we have seen how the energies are changing.
Okay, so here the spin orbit interaction effect is included,
yes.
But is then the dipole-dipole interaction included?
The dipole, No, it was actually not included in this.
Because that could easily be also extremely important effect, especially in these materials with a rather small spin-orbit coupling, because these materials are 3D element-based.
Yes.
At least from my own experience, I know that these could be equally important, and in some cases even a dominant effect, depending, of course, on the symmetry of the lattice structure.
Okay. Right. So I think in this case we need to look into more details. That certain calculation, according to your suggestion. Yeah.
Is there more time, or should I conclude?
1 minute.
Okay. Yeah. So then, maybe then a very simple last question about this subject. So suppose the reorientation of the moment takes place. How does it affect the deformation of the system, so the C/A ratio and the volume, and how does that finally then affect the magnetocaloric effects?
Well,
Can you give a concise but effective answer?
Sure, I will try. First of all, the magnetocaloric effect is mostly depending on the total magnetic moment and how it changes during the transition. So from figure 6.1, we see that it changes marginally there with the changes in concentration. So it will probably not change much the moment. However, this gives a better insight how the moment changes, how the direction changes, and this more fundamental point of view.
Okay, thank you very much.
Thank you. And the word is now to Professor Havenith.
Dank u wel, mevrouw de rector. Dear candidate, I have also read your thesis with a lot of interest, and I would like to start our discussion on figure 4.7 on page 53, where I hope you can fill in some details for me. So you excite a core electron to conduction band, I suppose, and you can generate different states, and that gives rise to different peaks in your spectrum. And can you tell me which peak belongs to which final state in the figure?
Honored sir. This is really not mentioned in this thesis, which peak should be corresponding to which one. And in short, I don't have the answer right now, so which peak corresponds to which state.
Okay.
But I really need to look into that and can answer to you.
Okay, and then I would like to ask you, you do DFT, and you have a high spin atom there, and you excite a core electron, so you end up with various spin states, and not all of them are fully the high spin state on the local atom. So you don't use proper spin functions if you do your DFT, probably?
No.
And can you give an estimation of the error that you create there? Is it negligible, or?
Did you understand the question?
If you can kindly repeat the last part.
So if you excite a core electron from your 1s,
Yes.
and you have, for example, your metal atom in a high spin state, let's say there are 2 electrons spin up, and then you create an excitation, then you have a spin up, spin up, spin up, spin down electron. And if you do DFT in a local density approximation, you don't generate the pure spin functions.
Yes.
So that will influence your energy. And my question was actually how accurate are these energies if you would correct for it? What is the error margin?
Okay. Yeah, the final state for this particular calculation, yeah, we how we do it, we basically in the electronic structure, starting electronic structure, we remove just one electron from the one state in the calculation, physical calculation itself, and put it in the valence band there, and then do the self-consistent cycle calculations, and let's see at the end how many electrons are finally in there. So it's, as you suggested, it's not always the full number, not the integer all the time, and that difference is always within the energy accuracy that we consider in our calculation. So which is around 10 to the power minus 4 electron volt in general. Yes.
Okay.
Could you, yeah?
Do I have...
Just a very, 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 very short question, if you can, or just leave it.
You have considered in chapter 2 many different compounds, and you have calculated energy differences and magnetic moments. And I was wondering if you could tell me which one of those compounds would be the best for your desired application.
Yes. So this one...
Short question, short answer.
Yes. So definitely there is no direct answer to that, because all of these different compositions can be used in different contexts. So cobalt, chromium, etc. can be used for different contexts. It has experimentally also, when it was generated, for a certain purpose. So yeah, there is
You're
not a
satisfied
better
with
or
the answer?
worse.
Yes.
Yeah.
Thank you very much.
Thank you. So we close the opposition with the co-promoter, Dr. De Wijs.
Yes. So, dear candidate, I also, of course, well, I read this more than once with great interest. Yeah, to ask a question, let's go to chapter 5. And I have maybe a very small one. On page 73, you show that you need to include the 0-point motion energy in order to get the energy order correct for the two phases. But that is a phonon effect. And then I'm wondering if that is important, should there also be a temperature effect?
Yes. Answer, there should be a temperature effect there, and it's better that we do a full-scale phonon calculation for that to correctly predict that whether this is really occurring at that particular pressure or not, which, yeah, probably that need to be done before you actually can put it as a
okay, so you say that is because sometimes, of course, the temperature effect is a very provokes a very different part of the phonon spectrum than the 0-point motion effect.
Indeed.
Okay, then I hope I still have time.
Yeah, for
a
question, maybe even for an answer.
Okay, so I start a question then. If you look in this chapter, page 72 and 73, on the left-hand side, you have the volume energy curve, for example, in the left panel.
I'm afraid that he will not be able to answer anyhow.
Okay.
So, the defense is hereby concluded. The doctoral examination board retreats for its deliberation. No, I have to give you. Sorry, I give the floor once again to the candidate, Pinto in Harry.
So having defended my doctoral thesis to the best of my ability, I like to thank the rector and my supervisors, as well as all those who have honored the ceremony with their presence.
Okay. The doctoral examination board retreats for deliberation. The Council of Deans of Radboud University Nijmegen has decided to award you the degree of doctor. I invite Professor de Groot to discharge the task assigned to him. In the name of the...
Okay. In the name of the Lord, with the power entrusted by law to the Council of Deans, I hereby confirm upon you, Prasenjit Roy, born in Kolkata, the title of doctor from the Radboud University in Nijmegen, to which are attached all the associated legal and customary rights and duties with respect to the academia and society. As proof thereof, I present you with this doctoral diploma, signed by the rector and doctoral thesis supervisors and co-supervisor.
Okay. Please be seated, and Professor de Groot will read the laudatio. Maar stand, misschien niet.
Dear Prasenjit, waarde doctor, it's a great pleasure for me to congratulate you with your just obtained PhD degree. Also, I'd like to congratulate your parents and your girlfriend. When the project started, we were looking for good candidates. You came to Nijmegen for an interview. You made a mature impression when you presented and discussed your master thesis work. It was a clear and easy decision to hire you for the project. Once started in Nijmegen, you have shown a good development. Your research topic was materials for magnetocaloric cooling. As your thesis shows, you were able to handle a substantial variety of subtopics requiring a variety of software packages. You used these successfully to carry out a series of very specific studies. You've put out ideas on mixed magnetism on a more firm computational basis. You did so when calculating the actual latent heat for manganese, iron, phosphorus, silicon. Together with the people in Delft, you also played an important role in the experimental verification of the mechanism of mixed magnetism. Moreover, you've studied many other aspects like the effects of doping, XMCD spectra, adding to the wide breadth of your thesis. I'm very happy with the results that help to further develop the field. I already briefly mentioned the collaboration with Delft, which was instrumental in setting up a project in the first place indeed. Indeed, I also mention BASF and their support of the FOM Industrial Partnership Program. I especially like to thank Professor Brück from Delft and Dr. Racing from BASF. Of course, I also want to thank you for collaborators that help making your research a success. I already mentioned the wide scope of your thesis before. In the past years, we have learned that as a person, you also have a wide range of interests, ranging from motorbikes, a whim, to you abandoned soon, to flying, something you have actively pursued in a glider airplane, music, and as we learned from the cover of your thesis, also painting, and I left much unmentioned. You're also a sociable person, an asset for the old ESM and now theoretical chemistry group, and always bring a good atmosphere in the group. Recently, you have made a transition from academia to real life and started to work on it for a company in the branch of cybersecurity by increasing importance in the future. To wrap up, it was a great having you in the group. You did a valuable work. I'm confident about your future. Hope you continue contributing to society and wish you and your girlfriend the best of luck.
Dear Doctor, I want to extend you the congratulations of the Council of Dean and the University. And we close by a prayer, so please stand. Gratias tibi agimus omnipotens Deus pro omnibus beneficis tuis, qui vivis et regnas per omnia saecula saeculorum.